If you could see the universe not as a collection of beautiful telescope images, but as a living system unfolding through time, the first thing that would strike you is not birth, but fading. We tend to think of galaxies as star factories, places where new worlds are constantly forming, where cold gas contracts under gravity and ignites into new suns. That's true, but only for part of the universe. Because alongside those galaxies exist others. Enormous, massive, ancient, and completely silent. Astronomers call them red and dead, and that's not a metaphor. It's a literal description of their condition. In these galaxies, not a single new star is being born. Their light is the light of the past, accumulated over billions of old, cooling stars slowly living out their age. And the longer you look at them, the clearer it becomes. What you're seeing isn't simply old age. It's a stoppage. The strangest part begins when you realize that, by all known laws of physics, such galaxies shouldn't simply switch off. The universe is full of gas, the primary raw material for stars. Gravity hasn't gone anywhere. Enormous clouds of hydrogen continue to exist even in old systems. Everything needed to birth new stars seems to be there. But no stars appear. As if someone pressed an invisible stop button. To understand how strange this is, we need to return to the most basic process, the birth of a star. In interstellar space there are cold gas clouds, nearly invisible but containing colossal masses of matter. If such a cloud begins to contract under its own gravity, its density grows, its temperature rises, and at some point a thermonuclear reaction ignites. A star is born. This process should repeat again and again as long as a galaxy has gas. And gas is genuinely abundant in the universe. So when astronomers began observing galaxies where star formation had completely stopped, it looked like a violation of the rules. At first, simple explanations were attempted: a galaxy ages, gas gradually depletes, and the process naturally winds down. But observations quickly showed this wasn't it. Some dead galaxies still have gas. And not in small quantities. It simply doesn't work. It doesn't contract. It doesn't cool. It doesn't become stars. This is where one of the most powerful and unsettling forces in the universe enters the picture: supermassive black holes. Today we know that nearly every large galaxy harbors one at its center. For a long time it was thought that such an object influenced only nearby regions. But it turned out that under certain conditions a black hole can control the fate of an entire galaxy. When gas begins falling into it in earnest, an accretion disk forms, a structure where matter accelerates to enormous speeds and heats to extreme temperatures. At that moment the black hole ceases to be black in the familiar sense. It becomes a source of colossal energy. An active galactic nucleus emerges. Powerful jets, streams of radiation, and shock waves burst from the center, spreading across tens and hundreds of thousands of light years. And this energy begins to act upon the galaxy itself. The cold gas from which stars should form gets heated. And heated gas loses its ability to contract. It expands, grows diffuse, sometimes is ejected entirely beyond the galaxy's bounds. Even if it remains inside, it can no longer perform its primary function. This is the process astrophysicists call feedback. And it can literally strangle a galaxy. The most alarming part is that such a mechanism can sustain itself. The more gas falls into the black hole, the more active it becomes. The more active it becomes, the more forcefully it heats and expels the surrounding gas. At some point, the system reaches a state from which return is nearly impossible. The galaxy loses the ability to cool. Even if gas remains within it, that gas is already too hot and unstable. It's like having fuel that cannot be ignited, but black holes aren't the only explanation. There are galaxies where their influence is insufficient to fully account for what's happening. Scientists then turn their attention to environment. Many galaxies don't live in isolation, they exist in dense clusters, where space is filled with hot intergalactic gas and the galaxies themselves move at enormous speeds. When a galaxy passes through such an environment, its own gas can literally be torn away. This process is called ram pressure stripping. Imagine a current tearing an atmosphere from a planet. That's roughly how a galaxy loses its gas. Without gas, no new stars. And again, we have a dead system. Sometimes the cause is a galactic collision. In the early stages, such events trigger powerful bursts of star formation, gas contracts, thousands of new stars appear. But then everything changes. Vast quantities of gas rush toward the center, feeding the black hole. It activates and releases energy that definitively suppresses any further star formation. A paradox results. The event that initially creates life ultimately destroys it. Gradually, the picture becomes clearer. Galaxies don't die simply of old age. They switch off due to processes that disturb the balance between cooling and heating. But the central question remains, is this final or not? Observations reveal something strange. Some dead galaxies occasionally show signs of life. Very faint, localized, but real. Small regions appear where new stars are actually being born. This means the process may not be entirely irreversible. One possible mechanism is the arrival of fresh gas from outside. A galaxy may capture a small satellite system or receive matter from intergalactic streams. If this gas manages to cool, it may restart star formation. But in most massive galaxies, this is nearly impossible. The surrounding environment is too hot, and any new gas quickly loses its properties. Another scenario involves the cooling of already heated gas. In the centers of some galaxies, processes are observed in which hot gas gradually loses energy and begins to flow inward. In theory, this should revive star formation. But as soon as it begins, the black hole reactivates and reheats the gas. A closed loop results, in which the galaxy seems to attempt revival, and each time stops itself. Looking deeper into the universe, things become still more troubling. We see that dead galaxies existed when the universe itself was far younger. Some of them switched off only a few billion years after their births. This means the mechanisms capable of killing galaxies operate very early and very efficiently. And then a thought arises that changes everything. Perhaps the death of a galaxy is not an exception, but a normal stage of its evolution. Perhaps most galaxies pass through this state sooner or later. Which means we are observing not an anomaly, but a pattern. And the question becomes global. If stars stop being born, what happens to the universe as a whole? Stars are not merely sources of light. They are factories of chemical elements. It is in their cores that the substances are forged from which planets, oceans, atmospheres, and all living things are made. Without new stars, the universe gradually loses the capacity to create anything complex. It grows colder, darker, and simpler. And if the switching off processes continue, this may mean the universe is slowly moving toward a state in which nothing new will ever appear again. Only old stars, gradually going dark. Only residual glow. Only silence. And perhaps the most troubling thing of all is that we still aren't certain we understand all the mechanisms behind this process. Black holes, environment, collisions, these are only part of the picture. There are hints of more complex factors: the distribution of dark matter, the structure of galactic halos, hidden processes of cooling and heating that we are only beginning to study. This means that somewhere in the universe there may be ways of switching off galaxies that we haven't even guessed at. And when we look at red and dead galaxies, we are in fact looking not only into the past. We are looking into the future of the entire universe, into a state where the lives of stars end not with an explosion, but with silence. And if you look even deeper, a sense emerges that we have only begun to understand how finely tuned this balance between life and death of galaxies truly is. Because in reality everything comes down not to one mechanism, but to a complex system of factors that can amplify or suppress one another. For instance, a supermassive black hole can behave in completely different ways at different periods. In one phase it barely affects its galaxy, in another it becomes an energy source capable of altering the galaxy's fate. And this doesn't happen just once. It can repeat like cycles of activity lasting millions, even hundreds of millions of years. It turns out that a galaxy doesn't simply die. It may pass through a series of blows, each more powerfully suppressing its capacity for star formation, until at some point a point of no return is reached. But even this point, strangely enough, may not be an absolutely rigid boundary. Because new observations show that in some systems considered fully passive, traces of cold gas are still found, and not merely residual gas, but structured gas potentially capable of participating in star formation. This calls into question the very idea of a final death. Perhaps it's more accurate to speak not of death, but of deep dormancy, from which, under extremely rare conditions, emergence is still possible. And then everything comes down to probability. How often can such conditions arise? Because for a galaxy to awaken, many factors must coincide: an influx of cold gas, the absence of strong heating from the nucleus, a stable dynamic that allows this gas to compress. And even if all these conditions are met, the result may be very modest, just a handful of new stars against a backdrop of billions of old ones. But even that matters, because it means the process is not completely blocked. And here another thought arises, discussed in astrophysics. Perhaps we underestimate the role of weak, slow processes. We are accustomed to seeking dramatic events, flares, collisions, active nuclei. But what if the fate of a galaxy is determined to a greater extent by quiet, nearly imperceptible changes accumulating over billions of years? Gradual shifts in gas density, slow redistribution of matter, faint gravitational interactions with neighboring structures. None of this looks dramatic in the short term, but on cosmic timescales it may be precisely these processes that decide whether a galaxy lives or fades. And the more we think about it, the clearer it becomes. The concept of a dead galaxy is a simplification. In reality, it is an entire spectrum of states, from fully active systems to nearly fully suppressed ones, with countless intermediate stages. Each of these stages can last an extraordinarily long time, so long that to us they appear stable, even though they are in fact very slow transitions. And there is something genuinely troubling in this, because it means the universe may change so slowly that we simply cannot perceive it. We see only isolated snapshots and try to reconstruct a dynamic that unfolds over billions of years. And sometimes these snapshots contradict one another. Some galaxies appear completely switched off, others seem nearly identical but show hints of activity. We try to unite these into a single picture, but perhaps we don't yet have enough data to see it whole. And that is precisely why each new telescope, each new mission, each new observational campaign can radically change our understanding. Because the farther we look, the earlier in time we peer. And the more galaxies we see at different stages of their life and fading. And sometimes these observations reveal things that don't fit existing models, galaxies that look too old for their epoch, or systems that should have died long ago but are still forming stars. This means there are gaps in our theory. And these gaps are not mere details. They are perhaps the key to understanding how the universe actually works. Because if we don't fully understand why galaxies stop creating stars, we don't fully understand how structures form in the cosmos at all. And that means we don't fully understand our own origins. And here the subject of dead galaxies unexpectedly becomes very personal. Because the elements from which everything around us is made were once created inside stars. And if stars stop being born, that process stops too. The universe doesn't disappear, but it ceases to create anything new. And this is perhaps the most precise definition of its aging, not destruction, but a gradual loss of potential. And if you look at red and dead galaxies, you can say that we are seeing a future in which energy still exists, matter still exists, but the capacity to transform them into something new is disappearing. And perhaps that is precisely what makes them so unsettling. Because this is not a catastrophe, not an explosion, not an end in a familiar sense. It is a silence that comes gradually and stays forever. And yet, despite all of this, a feeling remains that the story is not over, because every time we think we have understood the limits of the possible, the universe shows us something that lies beyond those limits. And perhaps it is in those rare exceptions, in those strange galaxies that refuse to behave correctly, that the answer to the central question is hidden. Is the death of a galaxy truly an end, or merely one of the states it passes through in a far more complex and not yet understood cycle? And the longer we gaze into these systems, the stronger the sense grows that the familiar division between living and dead galaxies is only a convenient illusion, created by our desire to simplify an extraordinarily complex picture. Because in reality the boundaries are blurred, and every galaxy is not a fixed state but a process, frozen at one of an infinite number of possible stages. We see it as it was millions or billions of years ago, and we try to draw conclusions about what is happening now, but in truth we are observing only a single moment in its long history. And if we accept this, it becomes clear. Perhaps many of the dead galaxies we observe are not at their finale, but in a deep phase of suppression that simply seems final to us because of how long it lasts. Galaxies don't hang in the void at random. They are embedded in a gigantic cosmic web, filaments, nodes, voids. And a key role in this structure is played by something we cannot even see directly: dark matter. It emits no light, it doesn't interact with ordinary matter in the ways we're accustomed to, yet it is precisely dark matter that creates the gravitational scaffold within which galaxies form. And here a new hypothesis emerges. What if the fate of a galaxy, whether it will be alive or dead, is determined at the very moment of its formation? Not when stars in a black hole already exist, but far earlier, when its dark halo is only just assembling. If the halo is too massive, it may retain gas while simultaneously heating it to temperatures at which it simply cannot cool effectively. As a result, the galaxy receives an enormous reservoir of matter that it cannot use. It's like having a full tank of fuel, but an engine incapable of burning it. Such systems may appear doomed from the very beginning. There is an even subtler effect. When the universe was younger, streams of cold gas could flow directly into galaxies along cosmic filaments, fueling star formation. But over time, as structures grew, these streams began to heat up. They lost their cold nature. And galaxies that previously received a constant supply found themselves cut off from the source. They don't lose their gas all at once. They simply stop receiving new gas. And then the slow fading begins. Not an explosion. Not a catastrophe. It is a silence that arrives gradually. But there is a moment that unsettles even scientists. We observe galaxies that are already dead, yet continue to evolve. Their shape changes. Their stars interact. Occasionally weak mergers with other systems occur. But all of this happens without the birth of new stars. Which means a galaxy can be dynamically alive, yet physically dead. Like an organism in which processes are still running, but growth is no longer possible. And here another unexpected question arises. Can a galaxy die incompletely? Can there exist a state in which it will never return to active star formation, yet never become fully passive either? Some observations suggest yes. There are galaxies in an intermediate state, no longer blue and active, but not yet fully red and dead. They are called the Green Valley. This is a transitional stage that can last billions of years. And this matters, because it means the death of a galaxy is not a moment. It is a process. Long, complex, multi-staged. But even accepting this, the most troubling thought remains. If most galaxies pass through this process over time, does this mean the universe as a whole is moving toward a state where star formation has nearly ceased? The answer given by current models is not encouraging. Yes. We already live in an era when the rate of new star formation across the universe is falling. The peak of star formation was billions of years ago. Since then, the universe has been gradually cooling in a global sense. Each new generation of stars is dimmer than the last. Each new galaxy is less active. And red and dead galaxies are not exceptions. They are harbingers. If we imagine the future on extremely large timescales, the picture becomes almost frightening. New stars will cease to appear. Old ones will slowly go dark. White dwarfs will cool. Neutron stars will lose their energy. Black holes will remain the last dominant objects. The universe will become dark. Not due to an absence of matter, but due to an absence of processes. And yet, there is one detail that prevents us from drawing a final conclusion. We still don't understand all the mechanisms that can both switch off and potentially switch on galaxies. New observations, new telescopes, new models constantly add pieces to this picture, and sometimes shatter it entirely. Every time things seem to have become clear, a new anomaly appears. A galaxy that shouldn't exist. Gas that behaves in ways it shouldn't. A system that died, but somehow shows signs of life again. And that is precisely why the story of Red and Dead Galaxies is not simply a story about an ending. It is a story about the limits of our understanding. Because perhaps, somewhere out there in the depths of the cosmos, processes already exist that are capable not only of stopping galaxies, but of bringing them back to life. And if that is so, then the universe is far more complex than we think, and far less predictable. And perhaps, it has not yet said its final word. And if we continue looking still deeper, it becomes clear that we have only begun to understand how finely this balance is calibrated, because in truth everything comes down not to a single mechanism but to a complex system of factors that can reinforce or suppress one another at different moments in time. The same supermassive black hole, for instance, can in one era be practically dormant, and in another become the engine of a transformation that reshapes the entire galaxy. And this is not a one-time event. It can recur in cycles stretching across millions and even hundreds of millions of years, each cycle landing another blow, progressively weakening the galaxy's capacity to form new stars, until eventually a threshold is crossed from which recovery becomes vanishingly unlikely. And yet even that threshold, as strange as it sounds, may not be absolute. Because increasingly refined observations continue to uncover traces of cold, structured gas in systems that were long assumed to be entirely inert, gas that, under the right circumstances, might still participate in star formation. This puts the whole notion of irreversible galactic death into question. Perhaps death is the wrong word entirely. Perhaps what we're witnessing in these systems is something closer to a profound suspension, a state of such deep suppression that it resembles finality, but is not quite the same thing. There is one more factor that deepens the uncertainty: time itself. Not in the human sense, but in the cosmic one. The processes we are describing can unfold across billions of years, and what appears to us as a stable, settled state may in fact be an imperceptibly slow transition. A galaxy may be losing its capacity for star formation so gradually that no single observation could capture the change. If we could compress time, we might watch it dim the way a fire dims when starved of oxygen, not going out all at once, but fading, breath by breath, over an almost incomprehensible span. But we don't have that luxury. Instead, we gather fragments, snapshots of different galaxies at different stages. And we try to stitch them into a coherent evolutionary sequence. And it is in that stitching that the contradictions emerge. Galaxies that should be silent but aren't, galaxies that retain thin veils of gas when by all rights they should have none, systems whose nuclei are too quiet to explain the suppression we observe, and others that survived violent episodes of activity yet somehow held on to pockets of cold material. These are not footnotes. They are fault lines in our understanding. And they point towards something important: the internal architecture of a galaxy, how its stars are distributed, how it rotates, whether it has a bar or spiral arms, shapes how gas moves through it, and therefore shapes its fate in ways we are only beginning to map. In some configurations, gas flows efficiently inward, feeding the black hole and accelerating the galaxy's own suppression. In others, it lingers at the outskirts, where conditions for star formation can persist long after the center has gone quiet. Two galaxies that look nearly identical from the outside, embedded in nearly identical environments, can follow entirely different paths because the details of their internal dynamics diverge in ways that compound over billions of years. And beneath all of that lies an even finer level: the microphysics of the gas itself. How it cools. How it responds to ionizing radiation. How magnetic fields thread through it and resist compression. How turbulence disrupts the fragile conditions needed for a cloud to collapse into a star. These are not exotic considerations. They are fundamental to whether any given parcel of gas ever becomes a sun. And they are extraordinarily difficult to observe directly, which means our models carry uncertainties at their very foundations. The cumulative picture that emerges from all of this is not a simple one. The death of a galaxy is not a single event, nor a single cause, nor even a single process. It is the outcome of an intricate interplay between mechanisms that activate and fade at different times, that reinforce each other in some circumstances and cancel each other out in others, that operate across scales ranging from the turbulent interior of a gas cloud to the vast scaffolding of the cosmic web. Every galaxy that has gone quiet carries within it a unique history, a particular sequence of conditions and events that brought it to where it is. And that history is, in most cases, still only partially legible to us. What we can read clearly is the broad trend. Across cosmic time, the fraction of passive galaxies grows. The overall rate of star formation in the universe has been declining for billions of years, ever since it peaked in a period astronomers sometimes call cosmic noon. The universe was once dense with activity, collisions, mergers, blazing nuclei, cascading star formation across entire clusters. That era is behind us. What surrounds us now is quieter, and what lies ahead, if current trajectories hold, will be quieter still. The red and dead galaxies we observe today are not aberrations. They are the direction of travel. On timescales almost too vast to hold in the mind, the end point of that trajectory comes into focus. Star formation ceases. Existing stars exhaust their fuel and fade, the most massive first, then the rest, over trillions of years. White dwarfs cool toward invisibility. Neutron stars spin down. Black holes, the last structures of any consequence, eventually lose even their mass to the slow leak of Hawking radiation. The universe does not end in fire. It ends in a darkness so complete and so cold that the word end barely applies, because nothing remains to mark it. And yet, there is always an and yet when it comes to the universe. Because our models, however sophisticated, are built on incomplete data, and the cosmos has a way of confounding them. Galaxies appear that shouldn't exist at the redshifts where we find them. Gas behaves in ways that no current simulation predicted. Systems that were classified as fully quenched turn out, on closer inspection, to harbor faint but genuine star formation in their outskirts. Each of these anomalies is a reminder that our picture, however detailed it has become, is still a sketch. The mechanisms we have identified, AGN feedback, RAM pressure stripping, virial shock heating, the slow strangulation of cold gas streams, are real and important and well supported. But they may not be the whole story. There may be processes at work that we haven't named yet, operating on scales or through channels that our current instruments cannot resolve. This is what makes Red and Dead Galaxies something more than objects of scientific curiosity. They are records. Each one encodes, in the distribution of its stars, the chemistry of its remnant gas, the spin of its central black hole, the shape of its dark matter halo, a compressed history of the forces that silenced it. Learning to read that record fully, to reconstruct not just what happened but why, and in what sequence, and under what conditions a different outcome might have been possible, is one of the central challenges of modern astrophysics. And it is a challenge that matters beyond astronomy. Because the stars those galaxies will never form are stars that will never forge the heavy elements that seed future planets. The planets that will never coalesce around those stars are worlds that will never develop the conditions that, here at least, gave rise to something capable of asking these questions. The thread connecting the physics of galactic quenching to the existence of minds that contemplate it is long and indirect, but it is real. We are, in a very literal sense, the product of galaxies that did not go quiet when they could have. And understanding why some do, and some don't, and whether the ones that did might ever stir again, that is not only a question about the universe. It is, in the deepest sense, a question about us. And perhaps that is the most fitting place to leave it. Not with an answer, but with the question held open, because the universe, as best we can tell, is still in the middle of its story. The silence is spreading, but it has not yet become total. And somewhere in the regions we haven't yet observed, in the data we haven't yet collected, in the models we haven't yet built, there may be waiting the piece that changes everything we thought we understood. That is not optimism. It is simply what the history of this science has shown, again and again, that the universe is always stranger, always richer, always less finished than we imagined. And that the questions worth asking are the ones that don't yet have answers.